Oh, yeah, here we go into one of my very favorite lessons. We're going to start out with generating power series using geometric series? What? This is essentially all about how we don't have to use a Taylor series build to build more power series or known Maclaurin series to build other power series. We can actually use the sum of a geometric series to do it. Let's ride into this awesome adventure together. So this says, our goals are to master using the geometric series to represent functions with power series, and use differentiation and integration with the geometric series to represent functions as power series. In other words, this is another way to generate power series. It's cool. And it only works though if you have a geometric series to start. You'll see what I mean. So let's jump. Recall that a geometric series looks like this, right? You've got the infinite sum from n equals 0 to infinity of a sub of times r to the n. That expands out to something like this. You've got your initial value a, and then r to the 0 is just 1, plus ar plus ar squared plus ar cubed plus, and I could go on and on. You know I could. And that's going to be the nth term, which is ar to the n, and it keeps on going and going. And we know that the sum of this, as long as the absolute value of r is less than 1, this will converge to the first term over 1 minus r. We know that to be true. All right, now, and if you have questions about that, go back to chapter 9 where we talk about geometric series. This is cool stuff. Write the first 4 non-zero terms and the general term for the power series expansion for that. So we're just going to jump right into it. What? Well, here's the thing. 1 over 1 minus x. Isn't that basically in the form of a over 1 minus r? So if you have something written in the form of a sum of a geometric series, then we can make a geometric series out of it. So in this case, it's identical to this idea where that first term, a sub 1 or a sub 0, just a is equal to 1. And x is going to be our r value. It's in the place of r. Oh, okay. So here's the thing. Some people will write it right in sigma notation immediately, put it right in that format. Other people will expand it out. I like to go right to sigma and think I've got my first term, which is 1, times r, which is x to the n. That's the sum of this series, right? That is, right here is the sum of that. And so we start that at n equals 0 to infinity. And when we expand that out, we'll see that the first term is 1 plus, and then you multiply that by r, x plus x squared plus x cubed. And it says, right, the first 4 non-zero terms, that's this, and the general term, plus dot dot dot, plus x to the n, and it keeps on going. So there's my first 4 terms, non-zero, and my general term. So we'll talk about where it converges in a second, but the whole idea here is, notice that this fits the template of a over 1 minus r. Then I actually insert the values of the initial term and the r value into a times r to the n, and then I expand it out. That's how I technically do it. Some people will start out, okay, here's my first term, and then I'm going to multiply by that term again and again and again to expand out. That's fine too. Okay, so we've got ourselves with this. So what does this mean? That means that this series is equivalent to 1 over 1 minus x. Okay, well, more on that in a little bit, but this is actually equal to that. So it says, on what interval does our power series exactly represent g as n goes to infinity? That's another way of saying what's the interval of convergence. Well, that's very easy to find because it's a geometric series. The absolute value of r, which is equal to the absolute value of x, must be strictly less than 1. And that's going to occur when x is between 1 and negative 1. So there's your interval of convergence. So that's to say that this infinitely long series is equivalent to, converges to 1 over 1 minus x, that function, as long as the x values we plug into this fall in this interval. If it falls outside of that, we diverge. And I actually have a picture to go over that. Now, why is that useful? It's kind of like, well, why would I need an infinite series to equal to this if I can just plug numbers into that to start with? Oh, you'll see in later videos. We're just learning the tools right now. More on that interval of convergence though. So what all of this means graphically is, if you have a graph of 1 over 1 minus x, that's this graph right here and right here. On the interval of convergence, here we are, there's negative 1 to 1. Notice that the 6th degree polynomial, so I took that thing out to the 6th when graphing this, so that's the 6th degree of this thing out to x to the 6th, is this function. Notice how the polynomial approximation, 1 plus x squared plus x to the third, and so on and so forth, is perfectly in line with 1 over 1 minus x for a good bit of it. And then as we get to x equals, so this is kind of fascinating right here, as we get to x equals -1 and x equals 1, that's where the divergence begins. 1 over 1 minus x and the actual function start to really go away from each other and act differently. There you see how our power series diverges at that point, way away from the actual function. Isn't that cool? I think it's pretty neat. I think it's really neat. So that's the interval of convergence in action on the graph. And I told you here to check out the radius of convergence too. The radius of convergence being a distance, we're centered at 0, of 1. 1 and 1 in either direction. There's the interval right there. You see it in action. Oh, it's beautiful. Okay, let's do one more before we shut this video down. Write the first 4 non-zero terms in the general term for the power series expansion for f of x equals 5 over x plus 3 about x equal to 0. So the fact that we are centered about x equal to 0, we kind of glossed over that one in this first video here. We just found the power series expansion here. I didn't really say that it had to be about anything, but this was centered about 0. So in this particular problem now, we're told you need to have it centered about 0. Why is that important? Well, that means that our r value can't be like x minus 1 or x plus anything. It just needs to be at x. So you look at this and you say, well, it kind of resembles a over 1 minus r, but not quite. So we need to manipulate this to get to look like that. So I'm going to keep the 5 there, but I don't have a 1. Well, before I even get there, let me at least put the variable in the r spot. Then what I'm going to do is I'm going to divide everything by 3 because I want this to be a 1 and it's a 3. So I'm allowed to divide every single term, both the numerator and denominator, by 3. That's allowed. Notice that r value is still centered at 0. It's not an x minus 1 or an x plus 2 or anything like that. But it's not quite in the form of 1 minus, it's 1 plus. Well, remember, everything we do has to keep this value equivalent to that. So we're doing algebraic moves that keep this equivalent to the original equation, the original function. So now I'm going to make the plus a minus, because we can do that. So 1 minus a minus x over 3. Why do all this? Because we're still centered at 0, and we now have 1 minus r, and there's a. So here's your a, there's 1 minus r. So now I take note. My a value is 5/3. Very nice. My r value is going to be equal to minus x over 3. So as I showed you earlier in this video, I then go immediately to sigma notation. I'm going to start that thing at 0. My a term is 5/3 times r to the n. And again, what's going on in my head right here, just to put that there, is I've got n equals 0 to infinity of a times r to the n. So I'm plugging in a, I'm plugging in r, and then it asks this particular problem for the first 4 non-zero terms in the general term. So we'll expand this out. So the first term we know if we plug in 0 is 5/3. Then if I plug in 1, I'm going to get minus, and I'll get x over 3, right? So I'll get minus x over 3 to the 1 times 5/3. So that's going to be 5/3 times, and then it's just going to be x over 3. I already took care of the minus right there. So each time we're going to be multiplying by minus x over 3. So that'll be plus 5/3 is still chilling. This will be x squared over 9. We just multiplied by x over 3 again. So that's the first 3 non-zero terms, one more, minus the 5/3 is still hanging out. And we're going to multiply this by x over 3. The minus was accounted for. X cubed over 27. And you can simplify that down however you want. And then the general term, I'll do dot, 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 dot. It's going to be right here. It's just copying that. We already developed the general term. That was 5/3 times minus x over 3 to the n. And I had a little extra dot, dot, dot action there. So sue me. It still works. Okay, that's it. Not so bad. So I'll leave it at that. Another way of making a power series, we just made a power series for this, centered about x equal to 0 using the geometric series sum. The next video, I'll go over a couple other examples where we're not centered about x equals 0. It's a little more challenging. All right, I'll see you there. Peace.